Hello everyone, I welcome you all to the course AV Design, and our today's topic is twin coaxial rotors, twin tandem rotors, multi-rotor configurations. The vertical flight challenge. The fundamental principle, unlike we have fixed wing aircrafts, this rotary wing aircraft comes with lot of challenges. In that, rotary wing UAVs provide lift, propulsion and control through the rotating wings. These rotating wings are nothing but the blades which are placed on the top using a configuration of swash plate, and there is a mast which is vertical on which the blades are fixed. And one of the major challenge with this rotary wing aircraft is the blades which rotate in the clockwise direction or anti-clockwise direction. If it is rotating in clockwise direction, it will create a torque in the opposite direction and vice versa. So, in order to control the torque or to stabilize the aircraft, rotary wing airplane or unmanned aerial vehicle, we have to generate a counter torque. So, that's a major concern when it comes to a rotary wing aircraft. So, most of the drones or helicopters which we see, they come with a solution for this torque problem. So, we'll see that solution in the coming slides. So, the major problem is applying power to a rotor which creates a reaction torque which attempts to spin the fuselage in the opposite direction. For example, assume this is the rotor, and if this is rotating in clockwise direction like this, then it will generate a torque in the opposite direction. To balance this, we will be placing a tail here to ensure that a lift is generated in this direction to counter this torque, so that it is stable. It won't turn the fuselage in the opposite direction. VTOL utility. Vertical takeoff and landing and stationary hover are critical for restricted terrain, maritime operations and precise surveillance. Twin coaxial rotors. This is an example of twin coaxial rotors, Camo KA32A, where we'll find there are blades, two sets of blades on the same mast. This is the mast. This is the mast, and we'll have blades. This is one set of blades, and this is one set of blades which will be rotating. So it features two counter rotating rotors mounted on a single vertical mast. The fuselage torque is balanced internally as the two rotors rotates in opposite direction. In the previous slide, we have seen an example where a tail rotor was installed because a tail rotor was present to counter the torque which is generated by the single main rotors. Right. Here you can see there are two rotors which is rotating in opposite directions. One will be in clockwise direction and one will be in counterclockwise direction. So it balances the torque. And one more example for this twin coaxial rotors is ML Aviation Sprite. The key advantages of using twin coaxial rotors. The first one is symmetry and control. It offers near perfect aerodynamic symmetry, simplifying flight control algorithms compared to asymmetric single rotor designs. The power efficiency, up to 3 to 6% more efficient in hover than single rotors because no power is diverted to a tail rotor and swirl energy is recovered by the second rotor. The third advantage in this twin coaxial rotors is the compactness. No long tail boom or vulnerable tail rotor, making it idle. Right? So we don't have any long tail. Like in previous lectures, we have seen that there was a tail boom, long tail boom on which the rotor was placed over there. So in this, it is not having any long tail boom or vulnerable tail rotors here, and it becomes much confined spaces like ship decks. So this is an example of twin coaxial rotors, ML Aviation Sprite. We can see here there are two sets of rotor blades. One will be moving in clockwise direction, the other one will be moving in counterclockwise direction. Gust intensity. Due to symmetry, the configuration has the lowest response to atmospheric turbulence among all helicopter types. The design challenges in twin coaxial rotors, the very first one is the mast height. The mast must be tall, roughly around 0.3 times the rotor radius. So this is the rotor radius here, and this is the mast. Actually, this is the mast, and this is the zoomed version of mast. This is the rotor mast. So the mast must be tall, roughly around 0.3 times the rotor radius to prevent the blades from striking each other during the maneuvers. Mechanical complexity. It requires a complex counter-rotating gearbox and concentric shafts, passing control inputs through the lower rotor to the upper rotor, which is technically difficult. There are two large lifting rotors mounted one behind the other. This is an example of Boeing CH-47 Chinook. Here we have two rotors. This is rotor 1 and this is rotor 2. Okay. So lift can be shifted between the front and rear rotors by changing the collective pitch on each. The simple examples of twin tandem rotors are Boeing CH-47 Chinook, and there is one more Rotor H-21, which is also called flying banana. So you can see this this configuration. This is Rotor H-21, which looks like a banana. So because of its appearance, it is also called as flying banana. This is one more example of twin tandem rotors, which is Chinook. The key advantages of using twin tandem rotors are the CG range. It allows for a very wide CG range, making it ideal for heavy cargo missions where the load weight may vary or shift. Structural efficiency. Placing the lift at the ends of the fuselage reduces the bending moments on the central structure. Payload volume features a clean, long fuselage unobstructed by rotor masts at the center. You can see the Chinook 47. It has a sufficient place in the fuselage where the pilot is been seated, even the passengers are seated here. Then there is a vehicle and there is a tank which it is carrying. So it will have sufficient space when it comes to twin tandem rotors, because there is nothing called torque here, which has to be balanced with an additional rotor. Because of the presence of two rotors, one moving in counterclockwise direction and one in clockwise direction, it balances the torque which is generated in the clockwise direction. The design challenges. The rear rotor operates in the wake, that is downwash of the front rotor, which reduces its efficiency. This is often mitigated by mounting the rear rotor higher than the front one. The tandem configuration is structurally efficient only for very large aircraft, typically above 10,000 to 15,000 kg, and it is rarely used for small to medium unmanned aerial vehicles. Multi-rotor configurations and the revolution, the quadcopter. It typically utilizes 4 or more electric motors with fixed pitch propellers. There is a control logic where movement is achieved by varying the speed RPM of individual motors. Your diagonal pairs of propellers rotate in the same direction, increasing the speed of one pair relative to the other, which creates a net torque. Pitch and roll. Increasing the speed of rotors on one side while reducing the other side tilts the entire body. The key advantages of multi-rotor configurations: there are no moving parts except the motors and propellers, which lacks the complex swash plates, gearboxes, and hinges of conventional helicopters. Portability and cost. Simple mechanics lead to low production cost and high portability, driving the skyrocketing popularity of small scale systems. Flexibility. It is more flexible regarding CG placement and safer for indoor use due to smaller rotor diameters. These are some configurations of multi-rotor. This is Y6 configuration. This is tricopter. So is tricopter configuration, quad X configuration, quad plus configuration, hexa X configuration, hexa plus configuration. This is octo X configuration and octo plus configuration. So coming to this Y6 configuration or tricopter configurations, you can see that this rotor is moving in clockwise direction. This is moving in counterclockwise direction to ensure that the torque is being controlled. Whatever torque is generated because of this rotor and this rotor, it will be countered by the torque which will generate because of moving of these rotor 2 and rotor 3. This will be moving in counterclockwise direction. So whatever torque is been produced because of this rotor 1, it will be balanced with the rotors of 2 and 3. Similarly, for quad configuration, the opposite sides, the diagonals, will be moving in clockwise direction and these diagonals will be moving in counterclockwise direction. If this is clockwise, this diagonal will be counterclockwise so that it is balanced. Else, if this is clockwise, this has to be counterclockwise. So it will be vice versa. One diagonal will be clockwise and the other diagonal will be counterclockwise. Then coming to quad plus configuration, this axis will be clockwise direction, then this axis will be counterclockwise direction. Similarly, for hexa-hex configuration, rotor 1, this is 2, let's 3, 4, 5, 6, right? So the rotors 1, 3 and 5 are moving in clockwise direction and the others like 2, 4 and 6, they rotate in counterclockwise direction to balance the torque which is generated because of the clockwise movement. Same thing comes with the plus configuration. We have rotor 1, 2, 3, 4, 5, 6. Same here, 1, 3 and 5 will be moving in clockwise direction and 2, 4, 6 will be rotating in counterclockwise direction to balance the torque which is formed. Similarly, we have octo-S configuration. Here also, there will be 4 rotors which will be rotating in clockwise direction and the other 4 will be rotating in counterclockwise direction. And similarly, for octo plus configuration, we have same configurations and same conditions, 4 clockwise and 4 counterclockwise. How they vary, how they control the stability, how they move forward, how they move backward, how is the pitch up and pitch down, right moving, left moving, lift up and lift and then coming down. These all we'll see in the next lecture. How to fly a drone? These are the controls of a quadcopter. When, for example, let's take quad. In detail, we'll see in the next lecture. Here we'll see the how basic quadcopter being controlled. So if all the 4 propellers are running at high velocity, then we'll have lift up, and if the velocity is been decreased, then it will move down. So red is for high velocity, and green is low velocity or minimum velocity. Then coming to pitch. So if the quadcopter has to move in forward direction, the rear side clockwise and anti-clockwise direction rotors will be moving at high speeds, and the front 2 rotors will be moving at low speeds. It will be rotating at low speeds. Then vice versa, if the pitch has to be down, then the back rotors will be moving at low speeds and forward rotors will be moving at high speeds. Then we'll achieve the back pitching. Similarly, bend towards left, the rolling operation. So the left side rotors has to be at low velocity and right side rotors has to be at high velocity. And if it is bending towards right, then left one has to be at high velocity and right rotors has to be at low velocity. Then it will move right. So if this is high velocity, like high velocities will tend to pull down in that region. Like suppose if all these 4 are creating heavy velocity, then automatically it will generate a force in the upward direction. And when it is about talking about forward pitch and all, so this lift will be generated. In this case, this will be generating additional lift and this will be generating a minimum lift. So this will be higher. So this attitude will be little up and this will be nose down moment. And similarly for this will pitch down and this will go up because more lift is being generated here. So it will move like this in the upward direction and the quad will move down like this. Similarly for roll, if it has to bend to the left, then the right rotor should create more lift and left should have less lift so that it bangs like this. Same thing with the right. If they want to bang towards the right, then this lift has to be more on the left side and right side will be less, then automatically this will come up. Here it is this. Then same thing with the moving, the diagonals when it comes to yawing motion of quad, then these diagonal, if it is having low velocity and this is having high velocity, then it will move to the left and vice versa for rotating at the right. So these are basic controls of quadcopter, which we'll see even in the next lecture. The major design challenges for the quadcopter design is high drag. The configuration is not aerodynamically optimized for forward flight, leading to slow maximum speeds. Scaling limits. Control requires rapidly changing propeller RPM. Larger propellers have higher rotational inertia, creating a lag time between commands and actual thrust changes, which limits their effectiveness at larger scales. Safety. Unlike an helicopter, most small multi-rotors cannot perform auto rotations. A single motor or power failure typically results in an uncontrolled descent. Conclusion. When it comes to conventionality versus specialization, the single main rotor remains the standard for most medium-sized unmanned aerial vehicles due to its simplicity and maturity. But alternative configurations offer distinct advantages for specific missions. The symmetry advantage. Co-axial and multi-rotor configurations provide aerodynamic symmetry, which simplifies autopilot development and improves stability in turbulent air. Weight as the primary constraint. In all VTOL designs, weight is depth. Configurations like tandem rotors and hybrid tilt rotors carry significant weight penalties that must be justified by mission specific needs like heavy lift or high speed cruise. The future trends: quadcopters and multicopters are expected to dominate the micro to small unmanned aerial vehicle market as battery technology and computerized attitude sensing continue to improve. Thank you. These are the references used for this lecture. We'll meet in the next lecture. Thank you.